Ladies, today we're looking at section 1.6 in your textbook, inverse functions. This is a review from an Algebra 2 topic, so if it's something that you feel like you're strong in, feel free to go on and do the homework, but check your answers. So if there's a topic on the homework that you do not understand well, you know that you'll need to come back and watch the screencast. All right, so let's review what inverse notation looks like. Remember, if the function is f of x, then the inverse is f to the negative 1 of x, and you just read that f inverse. I've given you a function x plus 3, and I've given you some ordered pairs that meet the qualifications of that function. For example, if we plug in 1, we come out with 4. If we plug in 2, we come out with 5. So just some example ordered pairs. Now I want you to think about, if the original function is x plus 3, what's the inverse operation of adding 3? And if you said subtracting 3, you would be correct. Okay, so let's see what happens when we subtract 3. If we plug in an x coordinate of 4, 4 minus 3 is 1, and we have an ordered pair of 4, 1. Let's plug in an x coordinate of 5. 5 minus 3 is 2. Let's plug in an x coordinate of 6. 6 minus 3 is 3. Let's try one more, an x coordinate of 7. 7 minus 3 is 4. Now I'd like you to compare the ordered pairs in the original function to the ordered pairs in the inverse function. What do you notice? Well, we had an ordered pair of 1, 4, and in the inverse, the ordered pair is 4, 1. In the original, 2, 5. In the inverse, 5, 2. In the original, 3, 6. In the inverse, 6, 3, 4, 7, and 7, 4. So what happened? We can say that f and f inverse have the effect of undoing each other Positive 3 undoes minus 3. Minus 3 undoes plus 3. What else happened? I see that the domain of f was the range of f inverse. 1, 2, 3, and 4 were the domain of f. 1, 2, 3, and 4 were the range of f inverse. I see that the range of f is the domain of f inverse. And y'all please forgive me for this being sloppy. Something's wrong with the slate that I write on, and so it's very difficult to write on this, so I apologize. I see that the range of f, 4, 5, 6, 7, is the domain of f inverse, 4, 5, 6, 7. So what happens to the domain and the range when we switch from the function to the inverse function? Well, the domain and the range trade places. Okay, goal 1, find inverse functions and verify that two functions are inverses of each other. Okay, so let's look at f of x equals 5x. You could probably find the inverse of this without even following any steps. What's the inverse operation of multiplying by 5? And if you said dividing by 5, you would be correct. So f inverse is x divided by 5. Now, how do we verify that? To verify that, we show that f of f inverse of x is equal to x, and we show that f inverse of f of x is equal to x. How do we show that? To show that, we plug f inverse into f and simplify, and f of x into f inverse and simplify. If both come out to equal x, then they are inverse functions of each other. So let's try that. Let's find f of f inverse first. So we're going to take x over 5 and put it into the original function in the place of x. So that gives us 5 times x over 5, which does reduce to x. Okay, we're halfway there to verifying. Now we'll plug 5x into x over 5. So 5x divided by 5 does reduce to x. So we have verified that these are inverse functions of each other. An alternate way to verify is to graph the two functions. So let's graph these quickly. F of x equals 5x has a y-intercept of 0 and a slope of 5. So I would rise 5, go right 1, or down 5, left 1. Okay, and let's draw a line through that. Sorry, like I said, the board does not work well. There we go. Okay, so there's our function f of x. And now let's graph f inverse of x. So again, it has a y-intercept of 0 and a slope of 1/5. So up 1, right 5, and down 1, left 5. Okay, and let's draw that line. Okay, so how can I verify by looking at the graphs that these are inverse functions of each other? Well, there's a relationship between the graphs of inverse functions have a special relationship, and that is they are symmetrical across the line y equals x. Okay, so they are symmetrical. So here's f inverse, and they are symmetrical across the equation y equals x. So let's graph that. Y-intercept of 0, up 1, right 1, up 1, right 1, slope of 1. And do you see how as I plot this dotted line y equals x, I have symmetry on each side of it. So there are two ways to prove by plugging the functions into one another and reducing to x, or graphing and the two functions being symmetrical across y equals x. Let's try one more example. Find the inverse of f of x equals x squared plus 1 if x is greater than or equal to 0. And it's important to note that we're saying the domain is only greater than or equal to 0. Okay, well, in example A, when we found the inverse, I just talked you through it. What's the inverse operation of multiplication? And we said division. But in this case, I want to show you a more exact way to find the inverse operation. The first thing, remember, we learned that inverse functions x and y swap places. The domain and range swap places. So we will begin by swapping places with x and y. Remember, f of x represents y. So we're going to switch those and change the equation to x equals y squared plus 1. Now we will solve this equation for y. So to solve for y, we will subtract 1 and take the square root of both sides. Plus or minus the square root of x minus 1 equals y. Now remember, the original problem gave us parameters of the domain or restrictions, saying that x was greater than or equal to 0, meaning only positive. That means in step 3, we would only take the positive in front of the radical. If the domain had been x is less than or equal to 0, we would have taken the negative. Okay, so now that we've found the inverse, we need to show the notation. So f inverse of x is equal to the square root of x minus 1. And there's two ways to verify. Remember, we can verify by plugging into one another, and they should reduce to x, and by graphing. So let's verify by plugging into one another. So f of f inverse. So if I plug the square root of x minus 1 into x, that's the square root of x minus 1 squared plus 1. When we square the radical, it cancels, and we have x minus 1 plus 1 is equal to x. We verified there. Let's find f inverse of f. So we'll plug x squared plus 1 into the radical. So that's the square root of x squared plus 1 minus 1. The 1's cancel. The square root of x squared is the absolute value of x, which is still positive x. So we verified that way. Let's verify by graphing just to prove. So when we get ready to graph the function f, which is x squared plus 1, I'll make a quick table of values. I know when I plug in 0, x squared plus 1, 0 squared is 0, plus 1 is 1. I'll plug in 1, 1 squared is 1, and 1 plus 1 is 2. I'll plug in 2, 2 squared is 4, and 4 plus 1 is 5. Now, why am I only choosing positive values? Because of the given domain. So we have ordered pairs of 0, 1, 1, 2, and 2, 5. And there's the function f. Now let's graph f inverse. So I'll plug in, beginning with 0. If I start with 0, 0 minus 1 is a negative, so I know that 0 doesn't work. So let's try 1. 1 minus 1 is 0. The square root of 0 is 0. And look, my ordered pairs switched, so that verifies. If I plug in an x coordinate of 2, 2 minus 1 is 1. The square root of 1 is 1. That verifies. If I plug in an x coordinate of 5, 5 minus 1 is 4. The square root of 4 is 2, and that verifies. So let's plot those. So over 1 up 0. Oh, I see I made a mistake right there. Let's fix that. My apologies, ladies. Let's try that again. So if I graph f, it's 0, 1, 1, 2, and 2, 5. There we go. Sorry about that. Okay, and then if I graph the inverse, 1, 0, 2, 1, and 5, 2. And then I want to put in y equals x to check for the symmetry. And as I graph y equals x, I see that it goes right through the middle there. So that completes goal 1. I hope this has helped.